So I'm going to talk about enforcing exact group equivariances in the context of machine learning models. In particular, the motivation is to learn how to express invariant and equivariant functions that would give me a prediction, say in some image classification context or in some particle simulations where there exists some group that can act in the inputs and maybe in the outputs. And it happens that, for instance, if I have these flowers over here, if I apply a rotation by, say, 90 degrees, or maybe a reflection of my images, the classifier should give me the same prediction. So in this case, I have these flowers, and the classification is rose, and this classification is invariant with respect to rotations. F of g times x is equal to f of x. So if I'm training a classifier for images, I may want to introduce that symmetry into the model so that it can satisfy some symmetries that we actually observe. We also want to express equivariances. So here, say that I have this particle simulation for some time, and I want to predict how it will behave in the future. So I know that if I have my particle simulation and I apply a rotation to all my positions and velocities, then the particles prediction should rotate in the same way. So that's what I will call equivariance. So I have a group acting in the input and the same group acting in the output. In this case, in this example, the group act in the same way, but it could act in different ways. And I will say that a function is equivariant if f of g times x is equal to g times f of x for all g in the group and all x in the data space. So the idea, what I'm going to describe today, is how we can implement these symmetries into machine learning models, and how can we quantify how much do you gain by introducing these priors or these symmetries into the machine learning models in different examples. So why do we want to do this? I would say that one reason why we want to do this is because when we introduce these symmetries, we're introducing the correct inductive biases for the models, meaning that, say, if we know that the laws of physics satisfy certain symmetries, so everything that is correct in the world will have those symmetries, so introducing them to the machine learning models will give us the right inductive bias for the learning. And also we can quantify how much do you gain by introducing these symmetries in terms of sample complexity, meaning that you will need fewer samples to learn the same, up to the same errors, a smaller generalization error, and I will show you some examples where these introducing of these symmetries into the models will help us with out-of-distribution generalization. And I will say that there is also very interesting mathematical questions that we can address. And I will say that many of these questions remain open. So I think there's a lot of space to actually do some interesting math. So for instance, how can we learn invariances from data? How can we learn the symmetries from the data in a way that is practical and scalable, and we can introduce that to the design of the machine learning models? How can we design algorithms that exploit invariances and invariants? And I'm gonna spend some time in this talk explaining how we design these algorithms and how the quantification of how much do we gain by doing this versus the standard baseline of the standard machine learning models. So the examples that I would focus on today, I would say that the examples that we care about are based on images, on graphs, and on particle systems. And the difference between what you would do in each of these spaces relies on how does the space look like and how does the group action in that space look like. So depending on the space, like if you're looking at images, then the space is images, and then there's specific group actions that you would care to express in images. Graphs have different group actions, and particle systems have different group actions. So just the math that you would do depend very much on like what your application is. And in order to do that, I would say that in the space of images, there's a lot of work in group equivariant convolutional neural networks. We generalize the convolutional neural networks to equivariant functions with respect to group actions. And there's also these steerable CNNs. You can see many papers by Cohen and Welling and Whaler. There's many things going on in this space. For graphs, the group that one cares about is the group of permutations. I will describe a little bit more in the next slides. There's a lot of work in the space of graph neural networks. How can one parameterize equivariant functions on graphs? And then my main focus today would be in the space of particle systems, where we want to be invariant or equivariant with respect to rotations and translations and maybe permutations. And in order to do that, people have worked in using irreducible representations to parameterize the space of equivariant functions, and also using the invariants, which is what I'm going to present today. So before I start, I don't know if you have any questions. So I would say that otherwise I'm going to start with explaining what are the symmetries that one cares about on graphs. And basically, the idea is that if you're given a graph like this one, then you can write the adjacency matrix of the graph, or but the adjacency matrix is not unique. You can write many adjacency matrices by doing a permutation of the order of the labeling of the nodes, or the permutation of the order of the nodes. So, for instance, if I switch the order of the green and the yellow node, then I will find a different adjacency matrix that represents the same graph. So basically, A and pi transpose represent the same graph. So if we want to learn a function of the graph expressed as an adjacency matrix, then we hope that this function plays well with the action of permutations by conjugation. So basically, what we want is, for instance, if we're in a context of a graph classification problem, we want that the function applied to pi transpose is equal to the function applied to A. For instance, say what is the shortest, the length of the shortest path that visits every node. That is independent of the representation of the graph as an adjacency matrix. Sometimes with graphs, we don't want to just learn a scalar, like just a value, an invariant function, but we want to learn embedding of the nodes of the graph in Euclidean space. So in that case, the function, the embedding would be a vector in Rn times k, when n is the number of nodes and k is the size of the embedding. And so we want that if we do a permutation on the rows and columns here, then the embedding that we learn, it has the according permutation. So here, this node embedding H will satisfy that H of pi transpose is equal to pi times H of A, and this is equivariant. So yeah, and so if you see the action in the input is not the same as the action in the output, but the group is the same. So the question is, how can we efficiently parameterize the space of invariant and equivariant functions with respect to this action by permutations? So there are many ways people do that. The classical way people do it in the context of graph neural networks is via message passing. Basically, this message passing refers to a function that is a message function that each node sends to their neighbors. And there's also an aggregating function where when you receive messages, you aggregate them with this aggregating function. And then the message function is the same for everyone. That's the way it's implemented as equivariant, just because everyone uses the same function. And depending on the features that the node has, it can take different values, but the function is the same. And that is independent of the representation of the graph as a matrix, and therefore is going to be equivariant. You can think of it as a weight sharing, because it's just the same function applied to every node. And this way is clearly in equivariant. It satisfies the symmetries, but we will see that if it's not implemented in if it's implemented in a naive way, you may not be able to express many functions with this architecture. Okay. Another form of expressing invariant functions or equivariant functions on graphs is by doing spectral methods. So the idea is that if you are given a graph represented or a matrix, then if you take the top eigenvectors, these eigenvectors are an equivariant function of the graph, meaning that if I apply a permutation to the rows and columns, then the eigenvectors will have the same permutation applied to them. And this is a reason why, say, spectral clustering works. And we can define spectral functions on graphs as equivariant functions. And for instance, there's this definition by Bruna in 2014, where they say, okay, given a graph, I can consider the JCC matrix. The JCC matrix is, you can consider, well, say this graph is metric, so you can consider the SVD of this graph, and then apply a function to the eigenvalues, and then that is my function. That is one way of expressing equivariant functions on graphs. Another way to do it is by consider these spectral GNNs, which take a set of operators associated to the graph, like the identity, the degree, and powers of the adjacency, and then learn a way to combine these operators in a form of Laplacian, like regularized the Laplacian, which is like a linear combination of these operators. And then you learn how you combine these operators, in the sense that if you apply a permutation to the graph, then all these things get the same permutation applied, and then this Laplacian is going to be equivariant with respect to that. And then there's like a standard way you can construct a machine learning or like a class of functions that parameterizes or this like a spectral method on these regularized Laplacians. So I'm not going to go into a lot of details of how to do it, but basically the question is, okay, how do you parameterize a class of functions that are equivariant with respect to this action? And the question is how much are you losing, or how many of these functions you are actually missing by using this parameterization? And there's many interesting works in this space. For instance, there is this paper by Xu and collaborators in 2019 and Morris and collaborators in 2019, which show that if you write these functions on graphs as message passing, like the ones that I described like 2 slides ago, what happens is that if you just do like a very naive implementation of this message passing class of functions, then what happens is that these message passing neural networks cannot really distinguish many graphs. So for instance, if you take A to be a graph consisting in 2 disjoint triangles, and B a graph consisting on 1 hexagon, these 2 graphs are 2 regular graphs with 6 nodes. It will happen that for every choice of parameters of your model, you'll have that f of A is equal to f of B. So meaning that there's no really, this parameterization is not expressive enough. It doesn't allow you to distinguish graphs that are apparently very different. But yeah, and this is in connection with the graph isomorphism problem. Like these message passing neural networks are in correspondence with something called the Weiss-Fellowes-Lehman test for graph isomorphism, which cannot distinguish like k regular graphs with n nodes, with two graphs that have the same number of nodes and the same and it has the same degree for every node, and it's the same. So yeah, and then you can look at different classes of graph neural networks and see how expressive they are in terms of like what class of functions they can distinguish. And you can think of if you have two non-isomorphic graphs, does there exist a function in your class that distinguish these two objects? And yeah, you can construct a different comparison of different graph neural networks using this framework. Okay, and also you can use this to ask, can you construct a graph neural network that allows me to count, say, how many triangles or how many star-shaped structures? And in general, if you don't design the class of functions with the specific purpose of being able to do that, then you'll find that most architectures really cannot really count structures of that way, meaning that they are not expressive enough. So that's all I wanted to say for graphs. I'm gonna move to a different group action and a different space. And in particular, I'm going to focus on other symmetries of interest, in particular the symmetries of classical physics, like rotations, translations, and maybe permutations. And I'm going to try to parameterize the class of functions that are rotation equivariant or scaling equivariant, for instance. So there's many ways people implement these symmetries in machine learning. Today, well, I may describe a little bit how you use the irreducible representations, or maybe the generators of the ring of invariants. For this, this is based on our work in UNIVS 2021, which is called Scalars Are Universal. And basically, the idea is the following. How can we implement the symmetry? So I think that the most common way people implement symmetries is via data augmentation, which is basically say that you know that if this is your input, this is, well, say if you know what happens with in the training set, you have like a particle simulation and you have the predictions of this particle simulation, and you know that if you rotate, the prediction should rotate, then you can add this rotation of the training set and rotation of the output to the training set, and so use that for enforcing or promoting the symmetry being satisfied. That is what is called data augmentation. Just enlarge your data set to include the rotated versions of your training set and the rotated outputs, and that's like the thing that people I think in practice use the most. Another way to enforce the symmetries or partially enforce the symmetries is because these symmetries with respect to these local actions may be in correspondence with some conservation laws due to Noether's theorem. So then you can, if you know that there exists some conservation law, like conservation of energy or conservation of angular momentum, then you can include that as a constraint or penalized constraint in your optimization, and then hope that the symmetry could be implemented in that way. But what I'm going to focus on today is how do you enforce your symmetries via architectural design, meaning that you design a class of functions where every object in your class of functions satisfies the symmetries that you want. And that is done in many different ways. For instance, I'm going to show you a couple. I have a bunch of references here, but yeah, I'm happy to discuss more later, but yeah, there are many ways to do it. One way is by doing some kind of like generalization of the classical neural networks, like feed-forward neural networks, to express equivariant functions. The idea is that classical neural networks, you can write them as the composition of linear layers and nonlinear activation functions. And so basically what you say is like, well, what if I ask the linear layers to play well with my symmetry? So to be like, say, rotation equivariant. Well, if you restrict your linear functions to be, say, rotation invariant, then you won't have a lot of things to express, because you cannot be like, I think that you cannot write linear functions that are rotation invariant. So unless they're trivial. So then the trick that people use is to extend the action to tensor products of vectors, and then parameterize the linear functions that are equivariant on tensors, on tensor inputs. So basically they say, okay, now L, instead of going from RD to RD, is going to take a tensor of K, or the order K of RD, and then output a tensor of order K I plus 1 of RD. And then the action is going to be defined so that acting on this tensor product is equal to acting in each of the vectors independently and tensorizing them. And so the question is, how can you parameterize the space of functions that satisfy that? And the second question is, how do you write the group action, the activation function, so that is compatible with the group action? And so there are many ways to do it. One way is what Finzi and collaborators do, which is basically they say, well, all the linear functions that satisfy these equivariants are actually a linear space. So you can think of just considering enough constraints and then solving a big system of equations to find the parameterization of the space of functions that satisfy that. They have a very nice software package called EMLP that implements that, and is very nice, and we use this as a baseline for our code, which we do something different. Another way people do that is by using irreducible representations. So basically the idea is that the linear equivariant maps are in a one-to-one correspondence with the maps between representations. So then if they can write the representations of the group in terms of irreducibles, then they can use that to parameterize all the maps between the representations. And this is actually implemented, and there's two software packages that I know, one by Fuchs, he's the first author, and then another one with Thomas is the first author, and they have an implementation in like PyTorch or TensorFlow for for SO3 using this idea. The identification of the product representation with the irreducible representations is done by using the Clebsch-Gordon coefficients. And I think it's hard to implement in general, but they have it implemented for SO3. And there are many papers, like there's one by Dima Maron, where they show that this approach is universally approximate all SO3 equivariant functions if you can use arbitrarily large order tensors in these layers here. So yeah, so it's kind of like a Stone-Weierstrass kind of result. So if I went to technical in the past, like 2 or 4 or 5 minutes, I hope I'm coming back to something that is a little bit less technical. So let's see. So how do we do it? So I think that we can parameterize the space of invariant and equivariant functions in a simpler way. And as in the case of the particle simulations, I would say that it is a much simpler way. And basically the idea is just use the classical theory of invariant functions by Weil. The idea is the following. Say that we have n vectors in RD. These are our inputs. So for instance, the particle simulation that I showed you earlier. And then we want to learn a function that takes these n vectors in RD and outputs a scalar R in R. And this function is OD invariant, meaning that if I apply a rotation to my input vectors, so every vector is rotated by the same rotation, then the output doesn't change, right? So how do we do that? Well, the classical theory of invariant functions tells you that a function is OD invariant if and only if it is a function of the scalar products of the input vectors. And this is what I'm writing here. If and only if f is equal to f tilde of the pairwise inner products of the vectors for some f tilde. So basically, every equivariant function can be written as a function of the inner products, and any function that it can be written as a function of the inner products is invariant. Yeah. If I said equivariant, I should have said invariant because the action in the output is trivial. So that is a classical characterization of invariant functions. And then this can be extended to equivariant functions by observing that if you have n vectors in RD as your input, and the output is a vector in RD and it's OD equivariant, meaning that if I rotate all my inputs, then my output should rotate in the same way. Then we can show that H is a vector equivariant function if and only if H is a linear combination of the input vectors. So these are the input vectors. It's a linear combination of the input vectors where the coefficient functions are scalar invariant functions. So are like in the previous thing. Right. So that gives me a complete characterization. And I can tell you that this is, I wrote it for OD, but similar characterizations will hold for the special orthogonal group, the Lorentz group, etc. And this characterization can be easily extendable to translations as well, just because you can say, for instance, write the functions in terms of the vectors where you subtract the center of mass, or maybe you use the pairwise distances between the inputs. The Poincaré group, which includes translations of Lorentz transformations, and you can extend this also to make it permutation invariant as well. It's not very hard. But basically the idea says that if you have my input vectors, and say that I have n vectors in RD, I can construct my scalars scalar products, which are the inner products of the input vectors, and then learn these f1 through fn functions, which are the coefficient functions. I guess that I call them like tilde in the formulation that I had here, these ones. And then just do a linear combination of that and obtain my output. So this basically is just the entire approach. And that doesn't, like in this case, there's no need to use the irreducible representations because we have a complete characterization of the set of invariants of the ring of invariant polynomials. And this, so we can show that if this function is a polynomial, then you can express your coefficient functions as polynomials as well. And this is an if and only if. So a function is OD equivariant if and only if you can write it in this term for some f's that are scalar invariants. So you can write it in terms of the inner products. And that's a complete characterization. So why does this work? Well, this is just a particular case of some more general algebraic property, which is the fact that if we have a reductive group over C or R, we know that the algebra of invariant polynomials, you can write it in terms of what they are called the primary invariants and secondary invariants. So the secondary invariants form a basis of the algebra of invariant polynomials as a P module. So basically the idea is that every element, every invariant polynomial can be written as a polynomial of the primary invariants, a polynomial combination of the primary invariants times the secondary invariants. And in the particular case of the OD that I was doing this example before, we know that the primary invariants are the scalar products and the secondary invariants are trivial. And that gives us the characterization that we had before. So, so if we have access to the primary and secondary invariants for our groups, then we can do it. We can do this parametrization of the invariant functions with no need of using the irreducible representations that these people had before. The issue is that this doesn't always scale well, and it's not always known like a complete characterization of the invariants. Say, if I give you a group acting in a weird way in a space, I don't know what are the invariants, but maybe that's something that we can work out. But even if we know the invariants, it can happen that the invariants grow exponentially with the number of nodes. So, for instance, if we want to do the graph neural networks that I showed you earlier, and we want to just write what are the basis of the invariants for the action in this graph neural networks, what will happen is that the size of these invariants would grow exponentially with the size of the graphs, and that's not something that we can work on in general. But in the case of this, the actions by these Lie groups, then the size are still being controlled, and we can use this for parametrizing equivariant machine learning models in practice. So basically, that's the point. So I can show you an example here. This the example here, this double pendulum with springs. So this example was implemented in this paper by Finzi that I told you earlier. Basically what we did is they implemented their equivariance using their method that they call EMLP, which basically does like this composition of these linear layers using the learning the parametrization of the invariant spaces or equivariant functions on the fly. What we did is we took what they have done for this problem, and then we replaced the the implementation of their equivariance with the implementation of our model, and we compare to how well it performs. So in this example, they have like a double pendulum with springs. It's kind of small, but just like you have a red mass and a yellow mass, and they're connected with springs. And the question is to predict the trajectories of these masses. So based on positions and momentums of the particles of both masses. So this system is Hamiltonian. The Hamiltonian, which is the kinetic energy plus the potential energy, is conserved. It's a conserved quantity, which is equivalent to asking for some time translation symmetry. And what we did is we wrote this as an O3 equivariant, meaning that if we have the positions and momentums of the two masses and the gravity vector as an input, then the prediction is O3 equivariant. So if you have the gravity as an input, then you know that if you rotate everything, the gravity, oops. Can you still hear me? I don't know what happened.
Yes, we can hear you. Thank you.
I had like a moment, yeah, but
no.
Everything's good.
We can hear you. Yeah.
Okay, so the idea is you have this double pendulum, and then if you rotate the pendulum, then it's not equivariant. But if you rotate the gravity with the pendulum, then it's still equivariant, right? That's the idea. And so we implement this model. The learning of this model is an O3 equivariant function where the gravity is also an input. So you take the scalars. Basically, you take the inner product of the velocities with gravity and of the positions with the gravity as well, all the pairwise inner products, and you learn a function of these inner products. And we did it using two computational approaches. One is called neural ODE, and the other one is called Hamiltonian neural network. So basically, in these two approaches, the idea is that, or maybe I'll explain just how the Hamiltonian neural network works. The idea is, given all the vectors that go into play, like the positions and the velocities and the gravity, etc., you learn Hamiltonian from these things, and then you integrate the Hamiltonian to make the predictions. The Hamiltonian is an O3 scalar invariant function. So we can express this Hamiltonian in terms of the scalar products, as I showed in our characterization before. And then, so from this Hamiltonian, you use a ODE solver or a Hamiltonian integrator to produce the predictions, and then you can learn from that. And so in this example over here, in this plot, I'm showing you I'm showing a comparison between the EMLP, which is what we use for our baseline, with the scalars formulation. And we see that the scalars formulation have much smaller error. And also we observe that EMLP doesn't use the full O3 because they don't take the gravity as an input to their system. But still, even in that case, we see that this performs better. And also, this Hamiltonian neural network implements the Hamiltonian symmetry, and this neural ODE doesn't really implement the Hamiltonian symmetry. So adding more symmetries suggests that the generalization error is smaller. And and that's So another symmetry that we can incorporate is equivariance with respect to scaling, or units equivariant. The idea is that in this example of this double pendulum, we are predicting a Hamiltonian, and the Hamiltonian has units, the units of energy. In this case, kilogram meter square divided by second square. So if I make a transformation to my masses, where every mass is multiplied by 5, or every mass, instead of being expressed in kilograms, is expressed in pounds or something, then the prediction should change accordingly to that transformation. So that's something that we can write as a group action. The group is going to be a non-compact group that is going to be like R, like something like R greater than 0 to the K, where K is the number of units, different units. So in this case, it would be 3. And that you can enforce in the definition of your model. So how do you do that? Well, there is a classical theory in dimensional analysis, and the main theorem is called the Buckingham-Pi theorem, that says that if you want to express a function that is unit equivariant, then the way that you can do it is by taking your input features and then making a transformation that makes them dimensionless. So for instance, if you have the mass 1, mass 2, then both of them have units of kilogram, and then mass 1 divided by mass 2 is dimensionless. And then so you construct a basis of dimensionless features, then you make a prediction on these dimensionless features, and then you scale back to the output with the right dimension. So the way you can do it is by solving a system of linear equations over the integers, and to find this a basis of the dimensionless features. And then from the dimensionless features, you can learn dimensionless labels using an MLP or something simple, like a simple neural network. And we did this example, and we show that the dimensionless machine learning works in a comparable way with respect to the baseline. The reason why it didn't work as well, in my interpretation, is because when you do this transformation from the features to the dimensionless features, you need to divide by masses or by some things that have different units. And this transformation may be numerically unstable if you're dividing by something that is close to 0. So you have to do it with care. But what we can observe is that this model expressed as units equivariant, it generalizes to other settings where we didn't train. That I think we can write in terms of out of distribution generalization, and the idea is very simple, right? Like if I have my mass, my mass 1 and my mass 2 sample from like a uniform 0, 1, then M1 divided by M2 will have the same distribution whether M1 and M2 were sampled from uniform 0, 1 or uniform 0, 1000 or whatever. So there's many distributions in the possible training sets that maps to the same distribution in the feature space. And then that allows you to observe that there's some good performance in out of distribution settings. And I think that this phenomenon has not been formalized in general, and I think that there's interesting math to do regarding this like concept of out of distribution generalization, and it's related with the concept of domain adaptation as well. Okay, so I know that I'm running out of time, so I'm just going to show you one example to the application of these unit equivariant models to vegetation dynamics. So in this particular case, we have some dynamical system that has to do with the evolution of the vegetation depending on different parameters of the soil, and every parameters of this is a kind of like a case where units equivariance would make sense because every parameter of the soil has units, so we can construct a basis for the dimensionless features, and we can do some regression, and we can do some learning of the model in dimensionless space. And we have preliminary results that show that working in dimensionless space has much better predictions. And the future work would be to learn the differential equation from data using symbolic regression and units equivariant machine learning. And I have 1 minute left. So I'm not going to discuss the ideas of how much you can quantify, how much do you gain by imposing the symmetries. There's a very nice paper by Elizedi and Zaidi in ICML 2021 that has a very nice discussion of it. But the idea is basically that if your group is compact, you can project your solution into the space of invariant spaces, of invariant functions, and you always gain something in terms of generalization if you do that. I'm happy to talk about it offline if you are interested. Finally, I will say, as a summary of my talk, the goal that I wanted to convey to you, I hope it worked, is that enforcing exact symmetries in machine learning models leads you to better sample complexity, more generalization error, better out of distribution. And there's very interesting math questions about how can we enforce these exact symmetries, how much do you gain by enforcing them, and there's many examples that you can think of this in, like, for instance, graph neural networks is a very large space of research, and it has some specific equivariance with respect to specific group action, but also there's the classical physics also have some equivariance with respect to other group actions, and we can provide a simple characterization of all equivariant functions with respect to physically relevant group actions, meaning scalings and rotations and permutations. And there's many open problems that make this more scalable or universally expressive, etc. An applications domain. And this is it. This is my references, and let me know if you have any questions.